Yeah, no, like, really. Oh,
The engineering requirements used to include frequency. Statics, dynamics, and engineering similar.
good.
They were required courses.
They're not required, none of them are required, but I'm just doing it because I have, you know, my schedule, but I might. It's too much of a hassle.
Would the course be good for you?
Well, I'm taking it with platform and intro to theoretical. So I'm like,
Oh, whether I can bring up the whole.
yeah, that's.
Ah.
He's stuck in my room.
See that was there. Okay, line integrals and Green's theorem. Questions? Yes,
I have a question about the plus C's at the end of the,
when we're resolving our potential functions.
so I get the plus. So when you do the dx integral, you do the plus function of y.
Right.
So, and then when you get your final integral, so. Like, say you had to add something. Just. Do you,
Just pick one.
number 6 was just what I was talking about because,
So let's look at number 5.
okay,
Okay, so in number 5, our vector field is y squared e to the xy I plus quantity 1 plus xy e to the xyj. So here's P, here's Q. Right? So I look at PY, that's gonna be product rule. Derivative with respect to y, I get 2y e to the xy plus, leave the y squared alone. Derivative of e to the xy is e to the xy, derivative with respect to y for the chain rule is an x. I look at qx, which is again chain rule and product rule here. So the derivative of this is y times e to the xy plus, leave this alone, derivative of e to the xy is e to the xy, chain rule, derivative of xy with respect to x is a y. My first reaction is, well, shit, these don't look the same. But here, if I factor out, I can factor out an e to the xy, an e to the xy, and a y. So y e to the xy comes out, that leaves 2 plus xy. Right? Down here, I have a y and an e to the xy. If I factor that out, what am I left with? I'm left with 1 plus xy plus another 1. That's 2 plus xy. This is conservative. Okay. The integral of p with respect to x is going to be the integral of y squared e to the xy dx. Bleh. Oh, wait a second. It's not as bad as I think it is. This is e to the stuff. If I let u equal x times y, remember I'm doing my integral dx, then I do du with respect to x. Take with respect to x, I just get a y. So du is y dx. That means one of the y's gets sucked up when I do the integral. I would have had to divide that y out, why I have one y instead of two. Or your brow is still further talk to me.
Oh, that's good, never mind.
As soon as you start asking, you're like, oh, wait, no, okay. Like that. You solve your own question. Okay. Now I do the integral of q dy. So that's the integral of 1 plus xy times e to the xy dy. I'm going to break this up and do it as two pieces. I'm going to do this as the integral of e to the xy plus xy e to the xy dy. Okay, I'm integrating with respect to y. Again, I have this thing up here, right? U equals xy du dy is x. So du is x dy. Right? I got an x here. I don't have an x here. But as far as this entire thing is concerned, x is a constant. Right here, I'm going to multiply by a factor of 1. The x that's on top will go with the dy. So I'm going to get a 1 over x there. Now I'm annoyed. What's the integral here? I got to do integration by parts. Okay. Humble. I have to do integration by parts. I'm going to do it on a separate page because I run out of room in this corner here. That'll teach me to pick one I've never done before. I'll learn. Integral xy e to the xy dy. U equals xy du dy equals x du equals x. That's how I deal with this part. But now I can think of this as y. Oh, wait a minute. Let me do this like this. It's u e to the u, right? But in order to get the du correct, I need that extra factor of x, don't I? So I'll have a 1 over x out here to go with the du. Now I do integration by parts. What's the integration by parts trick? Oh, u equals u, dv equals e to the u du. If I did it as, w e to the w, I change letters, it doesn't really matter, does it? So I get uv minus the integral v du, which gives me 1 over x times x, y, e to the x, y, minus the integral of e to the u is e to the u, e to the x, y. Plus c. So far, so good. But this gets added here, right? That's this part here. So the integral of q dy is 1 over x e to the xy plus 1 over x times xy e to the xy minus e to the xy plus c2 of x. What lovely thing happens? Right here. And the x on the inside cancels the x, 1 over x on the outside. So really I end up with that. Yes? Wait a minute. What was the integral of pdx? The same thing. So do I have to add anything? This time, my potential function is y e to the xy plus a constant. Okay, so this didn't do what I wanted. It didn't give me an example where we got screwed up, right? So give me what you got as an answer in 6.
So integral for dx, I got y into the x plus the y constant. And then for dy, I got y e to the x plus e to the y plus the x.
Now, again, I'm assuming you've done all of this perfectly right. I'm assuming. Notice those pieces match. So I definitely need that in F. Can you find the e to the y in the upper line up here somewhere? Oh, this only involves y's, so it's hiding here. What's hiding here? There's nothing up here that needs to get hidden. It's just a plus c.
So when it's 3 variables, would you do a function of x, y, like x,
So if I'm doing 3 variables, then I do the integral of p dx, and I get stuff plus a constant, but that constant could have y or z. When I do the integral of q, stuff plus constant in x or z. And when I do the integral of r dz, I get stuff plus constant in x and y. It's missing the letter I integrated with respect to. Now, unfortunately for me, at this point in time, they have to tell me, hey, this is conservative. for me to do the three-way one. So if I go back and I look on example 5, right? Here's my vector field. Y squared is P. 2xy plus e to the 3z is Q. And R is 3y e to the 3z. So I do the integral with respect to x here, and I get xy squared. I do the integral with respect to y here, and I get xy squared, but then I get y e to the 3z. That's okay, because that'll fit up here in the constant part. Down here, I do the integral with respect to z, and I get y e to the 3z, because the 3 up here goes away from that 3. That's my u substitution. Plus a constant in x and y. So when I start trying to put all this together, I say, oh, I'm going to need that xy squared, and that'll fit into the third equation because it's just x and y. I'm going to need the y e to the 3z. That'll fit in the first equation because it's just y and z. And then there was nothing extra to add to the third equation. Textbook actually does this differently from me. And it bothers me because they don't tell me why they're doing it in the order they do it. And that's the part that usually pisses me off. So the other way to do this is to say, oh, I did an integral. Remember, I have P should be the partial derivative with respect to x, and Q should be the partial derivative with respect to y. So I say to myself, P. So F is the integral of P dx. I get stuff, then I can take the derivative of that. I don't have to do Claudeau's theorem because it told me it was conservative. And I don't have a test in 3 variables yet. I would like to take Claudeau's theorem and make it work for 3 variables. It's just going to take a lot more work. We'll work on that. That's Monday. I promised. But it really is just, I could do Claudeau's theorem 3 different times, right? I could do it for the x and the x and the z, the y and the z. No. Testing all of that and remembering what goes with what's annoying. There's a better way. Well, I think it's a better way, but it's really just Claudeau's theorem writ large. So once I do this, whatever I get out of this, take partial with respect to y. Compare to q. If I only have p and q, that makes more sense. But if I have p and q and r, then I should take the derivative of the thing I get with respect to y and z and do more comparisons. And they never tell me which one they're doing in which order and why. I'd much rather just say, oh, what's hiding where? I can always tell who's gone online to look at answers there and who's gone online to look at sources there and who's looked at the book, because you can find different versions and different orders in different places. They all work, but this partial derivative method, the order in which they do it doesn't always make sense to me. But if it makes sense to you, let's run with it. Zach, you're looking at me like I just hit you in the head with a fish. You okay?
Yeah.
Just this kind of blank stare going,
Yeah, I'm just gonna stick with that.
Go ahead.
No, yeah, I was just saying, that was kind of like, I don't know, I'm just thinking. But we could, I was. In 16.
For 3?
Yeah.
16. Okay.
I was just like. This would be. Like, so we would. I was like, I tried to use like, the book thing was confusing. When I
Right.
looked in the book, it was like, that was how, it was confusing me in the book's way of doing it, and then I think I'm just gonna do it. I'll do it. You did with all of
Yeah. So my reaction is just to do three single integrals and then try and match up the pieces.
Yeah.
Rather than, okay, I'm going to take the integral of the first one and then I'm going to take the derivative of it with respect to the other two variables and see where things fall. I don't like that at all. That's me. But yes, so in 16, integrate with respect to x, integrate with respect to y, integrate with respect to z, and then see the stuff fits where. As long as you keep remembering that the constants contain the other variable, the one we didn't use here.
Three, for like all three have X, Y, Z,
Great.
and then two have X and Z. And then there's like nothing else.
Okay. So I say to myself, again, I'm making the assumption you got x, y squared z plus x squared z squared, I think. And then in the first case, you'd have a constant in y and z, right?
Yeah.
But notice that when you do the second one, you would get a constant in x and z. Hey, that piece could hide right there, couldn't it? So if it doesn't show up, that's fine, as long as this piece shows up. And then down here in the third one, I'm going to get a constant in x and y, but it turns out both of those pieces show up, so there's nothing to add there. So it turns out I end up needing two pieces. I see all three of them in the here, right? X, y squared z shows up in all three of these. And then this piece is hiding here. But then when I do that integral, it's right there. So what's hiding here? Nothing. What's hiding here? Nothing. It worked.
So you should have two C's.
No. I just end up with what's in here is this piece, right? So I get x, y squared z plus x squared z squared plus, well, the only thing that could be in all of those would actually be a constant. It would be constant in all three variables. What was hiding? Where is, so I see this in all three, right? I see this in the first one. I see it in the third one. Where is it in the middle one? It's in here. So it's in there, but it's hiding in that plus C, isn't it? And then I say to myself, well, does anything need to hide here? Nope. Does anything need to hide here? Nope. I need to make sure that the same things can appear in every row. So where does this appear in this row? Right. I need to have all of these things in this row, in this row, and in this row. I'll explain it 8 different ways. We could also, that's the one I want to hear. But here now you see how I could do a partial derivative. I could say to myself, okay, the partial derivative of that with respect to y is, oh, it's 2xyz plus 0. So the partial derivative of this matches that. What's the partial derivative of this with respect to z? It's xy squared and x squared 2z. It matches. Do I need to add anything else? No, the partial derivatives matched up. So that's why the book does it with that partial derivative approach. Because it says, oh, the partial derivative of that thing matches these pieces. I don't need anything else. If there was something else needed, I'd have an extra term in Q or an extra term in R that I hadn't found in F, and I need to add that piece in. But it doesn't tell me which one to do first, which one to do second, which one to do third, because there are 3 variables involved, and do them all. We'll line up the integrals afterwards. The book I learned this from called it reconciling the antiderivatives. I want to make sure these line up with each other, these match. There's a place for everything in each one of the lines. We should have no irreconcilable differences. That was a movie back in the 70s. Anyhow, more questions. Yes, ma'am.
Do like one or two integration for 16,414.
16,414.
Is the region, yeah, it's like, like, it's weird.
Okay, so it says we're going to use the triangle from 0, 0 to 1, 1 to 0, 1 and then back to 0, 0. Okay, so let me just plot those 4 points. 0, 0, 1, 1, 0, 1. I go this way, then this way, then this way. Yes? Okay. If I were doing the line integral, is that positively oriented or negatively oriented? Because it's counterclockwise. Do you want to do this as a type 1 or a type 2? It's clearly not polar. Okay, if I'm going to do it dy dx, then I need y to be bounded by equations. I need x to be bounded by numbers. So, question for you. Y is bounded by equations. That means I need a top and a bottom. What's this equation? What's this equation? Bottom to top. What are the numbers for x? Because when I think of it dy dx, I don't care about the direction of the curve anymore. I just care about the region. Ignore the arrows now. Ah, it says we're no longer doing the curve, we're just doing the region. That means because if my curve had gone the other way, what would I have? I'd have a minus sign on the whole problem, wouldn't I? If my curve is oriented the wrong way, I may put a minus sign and it comes back around.
It doesn't affect the.
So in any line integral, I know this sentence to be true. If you think of the curve going the other way, that's the same as putting a minus sign up front, making the curve go the right way. So that's my cheat. If I'm ever stuck with a curve that goes clockwise in the negative orientation, I can just walk backwards and that puts a minus sign on. Now we're actually going to use that. Not in the next section, but in the section 2 from that there. Because one of the things that happens frequently is we look at the edge of a surface. So here, I have the surface of the solid, right? The edge of the surface is this circle. Now, depending on which way that circle is oriented, I might be going around it counterclockwise or clockwise, depending on where I'm looking, yes? I'm not going to turn it upside down, but if I'm looking from the bottom, oh, yeah, that's going this way. Crap, that's clockwise. So depending on where I am, or whatever this is oriented in, I may need that curve to go in one direction or the other. No, I really want it to be counterclockwise, not clockwise, because if I'm walking around this curve and I think of myself going clockwise, then the region is on my left. So I want to go around this clockwise. I don't want to do the integral clockwise, so I'll do the integral counterclockwise. I'll just put a minus sign. Weird. It's this idea of a positive orientation being on my left. The inside should be there. That tells me which way I walk around something. All right, more questions.
Why if you did something wrong?
In my integrals,
Yes,
so if nothing matches here, right? If nothing matches, do they fit in the other spots? Tell me what you got. Well, that's okay. We'll see whether or not it's. So you do the integral P dx. You got
x squared plus 4y to the negative 2. But we want
C1.
x.
No, because we're doing the integral with respect to x. C1y.
Yeah.
I just didn't know if it was y or y and c.
Oh.
Integral q dy. Yeah, so my problem is that this piece, that could be hiding in there, yes? This piece can't. That means this piece should be somewhere over here, and it isn't. There's a problem here. Or my vector field wasn't actually conservative in the first place. So when you do the py and the qx, did it work? Then yes, there's a mistake here. If you know it's conservative and you got this, then we have a problem. You said this was 18?
8.
8. So in 8, P is what? What's P? That's what I have for P and Q. Is that what you have? Okay. Well, I'm looking from here to there. I'm going, that's not right. That is definitely not the integral of this with respect to x. Okay. I would like you to note something important, how far you've all come. Remember, a year ago or longer, in Calc 1, we were just getting to integrals. This freaked you all the hell out a year ago. Here we are. Therefore, it's easy to make those kind of mistakes, but look at how far we've gotten. Okay, more questions.
For 16,419, is that a negative variable?
16,419.
Yeah.
We're doing one arch of the cycloid x equals t minus sine t, y equals 1 minus cosine t. Okay, I'm about to hit you with an important problem. What integral did you set up?
I did. The proposed integral of x dy.
Okay. That's my arch of the cycloid, right? So the integral has to be done over a curve. What's your equation for R of t? What did you use for x and y? I'm hoping you used these.
That's what I put in my equation in the.
Right? When you draw that curve, that gives you this. What's the problem? What else is the problem? There's two problems. You've only hit one of them. It is clockwise. We start here, we end here, it's not closed. There's another piece of this curve here. This is really curve 1. I need curve 2 to close this sucker up. But curve 2 is a straight line. I'm sorry. Not all the way. Remember, when I'm doing a straight line, I use that, right? But for this curve, we start here and we end there. What's the x value here? And the y value here, sorry, the x value here. So this is 1 minus t times 2 pi 2 pi comma 0, right? xy plus t times 0, 0, which makes r of t 2 pi 1 minus t comma 0. Now you have to do two integrals. You have to do the integral that way, and then you have to do the integral on this piece. You add those together and you say, wait, that's clockwise, put a minus sign on the whole thing. Because in order to do this Green's theorem area, you have to have a closed curve and you have to be going the right direction. The negative sign that you got comes from the fact that we didn't go the right direction. Which I have to have a closed curve also.
So you put a negative in front of C2 as well.
Yes. The integral over C x dy becomes the integral over C1 x dy plus the integral over C2 x dy, and the whole thing gets a minus sign in front of it. Because we're going the wrong way. Polar perimeter only works if I go and close. I will tell you though that the second integral turns out to be really easy. By the way, this is also a really good way to figure out the area of an ellipse. I know the formula for the area of a circle is pi r squared. The formula for the area of an ellipse is hard. When you do it this way, it turns out to be really easy. I think that's an example in the textbook. Used to be an example in the textbook. Yeah, page 1099.
Well, if I can see a lot of people have regular y equals 1/x. And then it gives you like the points. Need to use the y equals 1/x.
No. I would need to use the curve if I were actually doing the line integral. But if I can find the potential function and just use the ends, then I can just use the ends. So if your vector field is conservative, you don't need the y equals 1/x. If your vector field's not conservative and you got to do the line integral the long, ugly, nasty parametric way, then you need the equation. Please let it be conservative. More questions?
If you have a plus c in your f function. When you go to like do f of b minus f of a.
These cancel.
Oh.
Just like they did in the fundamental theorem of calculus back in Calc 1. Yay! That was the best part about about what we did with the fundamental theorem. You could use any C because you'd add the first part, you subtract the second part, you go. Make it 0, make it easy. Which means that the entire integral is this answer with the minus sign. But you have to have a closed curve. If you don't have a closed curve, you can't use the theorem. That's why, even though this number turns out to be 0, I can't do this without a closed curve. I know I made you do all this extra work. Why? Because it isn't right if you don't do the closed curve. It turns out to give you the right answer. Blind fucking luck. And I hate being lucky instead of being right. Look, I'm technically correct, but that's kind of correct. I did tell you that second integral was really easy.
Okay, back to number 8. Yeah. Okay, so I got an x squared and a y that match. And then there's like a 1 or negative 1 over y. No. I'm not getting the key.
I'm integrating this with respect to x. What you just told me was the integral with respect to y. You integrate p with respect to x. Over here, I'll integrate with respect to y. But over here, I integrate with respect to x.
Okay, but then if you got an x and a y. That you can't fit into
It can't fit into the constant, that is true. If I have an x and y, it won't fit in the constant. But then go over here and do this integral. I'm integrating this, right? What's the integral with respect to y of y to the negative 3? Over.
Oh, over 2.
So the 2 cancels. And I get. These are arithmetic errors, no?
Oh.
I think we all need a weekend in spite of the fact it was a short week. That's not right. See, we missed Monday and it just took our brains right.
Okay, they match and they don't fit into the constant.
Because there's nothing that needs to go into the constants. They're just turning into a plus C.
Is there just always gonna be a plus C?
Yes, I'm doing an integral, there's always a plus C.
Okay.
Every indefinite integral gets a plus C.
I'm worried about it if it goes into like an X.
Because sometimes it doesn't match up and we need to make sure stuff fits. There has to be a place for this in the second line. Where is it?
But are you just gonna have a plus C anyway?
I'm gonna have a plus C. Anyway. But where are the other things? The other terms all have to appear somewhere. It's not that this is always in here. This is always high, this plus C. But where are these things? It's not in the middle row. Oh, yeah, it's high. Every term has to appear in every one of my antiderivatives. Especially when they have letters mixed up. Like you said, the xy squared. This is the question you asked me. You said, hey, wait a minute. This piece, I can put it somewhere, but I can't put this piece somewhere. There's a problem here. And I said, you're right. There is a problem here. It's to reconcile the three different answers that I got, or the two different answers I got are really the same. I need to end up with one function. So I did this thing, I did this thing, I did this thing. That should all be the same thing. Do all the pieces in this part fit in this part and this part? Because I got to make this puzzle go together. And if I can't make the puzzle go together, it means there's a piece out of place. Why is there a piece out of place? In this case, the piece was out of place because we hadn't done uniform. But that the other reason is it's not conservative. Oh, that's why there's a piece out of place. Make sense?
Yes.
Okay, I will see you all on Monday. Have a wonderful rest of the day. Drew looked at the clock and went, oh, I'm over. Crap.